Hi there, my name is Abel Encarnacion. I'm going to make a quick presentation right here on layer carbides. Right here you can see a couple of the applications right here of layer carbides. They go from medical applications, energy applications. They serve for renewable energies in order to improve our environment. They also serve a lot in heat dissipation and some other applications I'll mention in a second. Layer carbides or MXenes. It's actually written, as you can see right there, MXenes. I like pronouncing it MXenes, it just sounds way better to pronounce. MXenes are a broad group of two-dimensional 2D metal nitrides and carbides holding a construction involving two or more multi-sheets of transitional metals. In the transitional metals would be the M right there in MXenes. These transitional M particles are crammed into a hexagonal 2D frame that are interseated by nitrogen and carbon layers. The carbon layers or nitrogen layers will be the X molecules into the MXene name. These carbon layers or X molecules, they lodge into the octahedral frameworks among the contiguous M particles. One funny thing about this is that layer carbides are not literally 2D, but they're in fact very thin since they only measure a couple of atoms wide. You can tell right there in the middle of the image, in between the MAX, you have the MXTX sheets of layer carbides, and you can tell right there they're maybe 1, 2, 3, or 3 atoms wide. A little bit of context in history. Okay. Max phases are 3D bulk layer precursors with alternating metal carbons and the A layers. So the MAX phases will be the precursors of the MXenes. These have alternated metal and carbon and A layers. From the A layers would be pretty much any element from the group 3A and 4A. That could be either boron, maybe aluminum, maybe germanium, maybe lead. Maybe any of those elements could become part of the max phases. Again, the max phases will be precursors over to the MXenes. MXenes are formed chemically by removing the A element or the A layers to reveal thin, conductive, and reactive nanosheets. The max phases layer ternary carbides and nitrides generally have the formula MAX, were initially explored in the late 20th century from the 70s all the way up until the 90s. They were explored for their unique combination of metallic and ceramic properties, including electrical conductivity and thermal stability. It wasn't up until 2011 that researchers at Drexel University, led by Yuri Gogotsi and Michael Barsum, selectively etched the A layer from the MAX phases by using hydrofluoric acid, successfully isolating a new class of 2D materials that we now know as the MXenes. These materials retain the layer structure of max phases, but exhibited enhanced surface chemistry, conductivity, and mechanical flexibility, making them highly promising applications in energy storage, electronics, and environmental technologies. Why are these layer carbides important? Among all of these benefits that they have, especially going from an MAX to the Maxines, is that they have way higher electrical conductivity. Maxines, like like that. Maxines can exhibit metallic conductivities up to 10,000 S over centimeters, rivaling or surpassing many other 2D materials. They also function well for energy storage. Their high, their high, sur- their high surface area, hydrophilicity, and tunable surface groups make them ideal for supercapacitors and batteries. They also have medical applications. Vaccines have shown promise in biosensing, photothermal therapy, and drug delivery due to their biocompatibility and functional surfaces. Vaccines can be synthesized from two different approaches. The one that's most common, usually used the most, is from the top down. A top down synthesis would be start with a compound that's already made and chemically alternate in order to turn it into something lesser. In this case, a top down, we're starting with something greater, which would be the max phase, the MAX phase. Again, including that A atom, that in this case would be a group 3A or 4A. In order to do this, we would chemically remove the A layer to isolate the 2D Maxine layer. This is done through an etching process, which I have it right here. Etching usually uses aqueous hydrofluoric acid to selectively remove the A side atoms, for like aluminum, for example. There's another safer alternative that uses in situ HF, or hydrofluoric acid, generated by mixing lithium fluoride with hydrochloric acid. This yields Maxine nanosheets So that is the top down. There's also the approach using the bottom up, which is starting with something very little and making it something larger. This will be a less common method of producing Maxines by aiming to directly build Maxines using chemical vapor deposition, or CVD, or using the other method, which is solid state reactions, bypassing max phases altogether. In the first option I mentioned, the chemical vapor deposition, or CVD, compounds of different metals and carbon that had been synthesized by reacting metal films with methane or acetylene under controlled conditions, or using solid state routes. Some efforts involve reacting metal halides with carbon sources at high temperatures. Using the bottom up offers a couple of advantages, such as offering precise control over thickness, composition, and structure. It could also avoid surface terminations introduced during wet chemical etching. Using the bottom up also could enable heterostructure and composite fabrication. That will give the molecule many other uses. On the other hand, going back to the top-down approach, its advantages include a much simpler and effective method to reach a product, and it produces higher quality functionalized nanosheets of the Maxine sheets. Going a little bit more into depth with etching with hydrofluoric acid. This method uses aqueous hydrofluoric acid, using right here the titanium aluminum carbide along with hydrofluoric acid in order to reach our product. Now, the safe alternative, which is the hydrofluoric acid in situ, this etching route is less hazardous than using concentrated hydrofluoric acid. It's less caustic. It's an easier reaction than using the full concentrated hydrofluoric acid. It also leads to the lithium intercalation between MXene layers, which facilitates the delamination into single or few layers. The resulting titanium carbide MXene has tunable surface terminations and higher colloidal stability in water. The morphology of MXene has various thickness and sizes, but usually MXenes are also thin 2D nanosheets. They're typically just around 1 to 2 nanometers thick for single layers. This corresponds to the thickness of 1 unit of MXM, so the transition metals are all around a carbon or nitrogen atom, creating something similar to a sandwich, as you can see all of these wafers in the image. One good example of this would be titanium 3 carbide 2, where the atomic layers are strongly bonded within the plane, but weakly held together between the layers. Lateral dimensions of these sheets can vary depending on etching and delamination methods, but often reach micron scale sizes of around 1 to 10 micrometers, especially when mild etching and careful delamination are employed. Alright. In the surface of the carbide sheets, different functional groups could be added onto it. During the chemical etching, especially with hydrofluoric acid or in situ hydrofluoric acid, surface functional groups naturally form on MXene sheets, whether that'll be a hydroxyl group, the OH, fluoride group, the F group, or the oxygen containing groups. This could be something similar to acetic acid or any other carboxyl group. These groups are not just passively, they strongly affect the hydrophilicity, electroconductivity, and interlayer spacing and interaction with ions, molecules, or polymers, giving your carbide sheet a lot of possibilities on what it could be used for. Essentially, why would we need to add a carbide sheet over to any functional group is to give the functional group a lot more flexibility, whether that is in thermal capabilities, or maybe just flexibility in order to enter another enzyme or protein for that matter. I'll get a little more into depth about the thermal and flexibility of the carbide sheets. Again, going back into the different functional groups that could be added onto a carbide sheet, they influence the properties of the carbide sheet in hydrophilic nature, making it maybe less or even more hydrophilic, depending on the functional group that you add. Also, by adding multiple or different functional groups, you can also increase the chemical reactivity for catalysis and sensing, or the cation intercalation, maybe adding a sodium ion or a lithium ion for energy storage. Now, carbide sheets also have high electrical conductivity. Maxenes like titanium 3, carbide 2 exhibit metallic conductivity with measured values up to 10,000 S per centimeter, among the highest for 2D materials. This conductivity depends on the type of transition metal and the number of layers. Surface terminations, for example, oxygen enhances while fluoride reduces conductivity. The conductivity also depends on the degree of flake alignment and delamination. The application of all of these high electrical conductivity could be maybe utilizing the carbide sheets for supercapacitors. These supercapacitors will have really high conductivity in a large surface area that would enable rapid charge and discharge cycles in order for a higher power density and better power output. The applications also range over to electromagnetic interference shielding. Carbide sheets and their metallic nature and layer structure make Maxenes excellent for blocking electromagnetic radiation in electronics and aerospace. This is highly crucial since you don't want any of your electronics to become fried by any sort of radiation that you could find in space, or maybe even in dedicated flight space. Carbide sheets also have multiple mechanical properties. They are very strong yet flexible. Maxene nanosheets possess high tensile strength and elasticity due to the strong transition metals with carbon bonds and their 2D flexibility. Since they're very thin, they don't have any width. Well, they not literally again, but they virtually don't have any width. It allows them to flex a lot, and the strong bonds between the transition metals and carbon keep it from breaking apart. Most of these carbide sheets have Young's modulus values ranging from 330 GPa up to 600 GPa, comparable to steel, but also thin and flexible. The applications of such a strong yet flexible object is that we could use it in polymer composites. Reinforcement with Maxenes could improve mechanical strength and conductivity and barrier properties for a variety of projects. We could also make flexible electronics with carbide sheets. We could make films that maintain performance even under bending or twisting in order to keep machines flexible and maintain all of those moving parts completely functional. Maxenes also have various chemical properties, for example their surface reactivity. Maxenes are chemically active due to surface terminations. Again, we'll go back into the functional groups, such as the hydroxy, the fluoride groups, or any carboxy groups. All of these could promote the ion exchange, also absorption of molecules and catalytic activity. All of these could be applied to produce sensors for using the surface group to enhance biomolecule binding for glucose, dopamine, and heavy metal detection. All of these surface reactivity could also be used for water purification, where MXenes could absorb heavy metals, dyes, and radioactive ions due to their charged high surface area surfaces. They could also be used in catalysis. One good example would be CO2 reduction due to turnable sizes. Alright, carbide sheets also have very good thermal properties. Their thermal stability is among the best. Most MXenes are thermally stable in inner atmosphere up to 6 to 800 degrees Celsius, depending on the surface terminations. The composition often starts with loss of the hydroxide or fluoride groups around 300 to 500 degrees Celsius. Then the oxidation of the carbide backbone begins in temperatures over 500 degrees Celsius. You can see right here in this image is an example of how well a MXene sheet dissipates heat. The blue layer at the bottom will be a completely cooled down MXene sheet, while we have the temperature measured on the left and the time it takes for it to completely cool down. You can see we have picoseconds, nanoseconds, and microseconds. After about a couple hundred microseconds, it will be completely cooled down. But essentially, we have a red arrow, which will be a pump. Think about it as a laser heating up an electron, exciting an electron, which then travels onto the carbide sheet, and then essentially passing down that electron from the first carbide sheet up onto the next one. Furthermore, then the yellow arrow will be a probe that measures the temperature in order to test how the surface cools down momentarily. This thermal stability of carbide sheets has a couple applications, such as thermal management. The MXene-based composites can dissipate heat in microelectronics. Could be very useful in groundbreaking technology with CPUs, for example, who often heat up on their high stress. Carbine sheets could also be used for fire retardant coatings, since MXene slow flame spray by forming insulating char layers once they burn down. So, in conclusion, MXenes are a tunable family of 2D transition metals, carbides, or natrides that involve high conductivity, high surface functionality, and have versatile mechanical and chemical properties.